Okay, so welcome everybody for the Quasiworld seminar. So we had a long summer break. So we have two speakers today. So our first speaker is Tuomas Sahlsten from the University of Helsinki, and he'll talk about Fourier-dimensional and convex cocompact hyperbolic manifolds and dynamics of rational maps. So please, Tuomas.
Yeah, thanks for the invitation. It's nice to give the talk with this audience. And it actually turns out that I gave a similar talk today in the Helsinki local seminar. I was actually asked because some of them were not able to join this online one. So I got already some questions from there. So I hope to continue a little bit similar. Now I know kind of where I end up. So this topic is about hyperbolic manifolds and a little bit about rational maps, and a little bit go into some quasi-regular things that we are thinking about at the moment. But hopefully maybe there are some questions from the audience on this. And this is a joint work with Simon Baker, Osama Khalil, and another paper that we're talking about, my postdoc Gaetan Leclerc and PhD student Sampo Paukkonen. So I'll go a little bit in an assumption that you've seen a little bit of hyperbolic geometry, but let me revise that slightly. So what we have here is a geometrically finite hyperbolic surface. You could think about, let's say, one example would be like a convex cocompact surface, like in this picture, where we have a group of isometries of the hyperbolic plane given by the Möbius transformations. And when you are given this Möbius transformation, you could have this reflection, for example, that would connect these opposite, like let's say, for example, the opposite semicircles that intersect orthogonally at the boundary. And by doing this gluing together, like in this picture, we end up with a three-funneled surface. That's a hyperbolic surface, and I'm kind of interested of the kind of connections to fractal geometry that seem to arise here. So the limit set arises by essentially like iterating this construction that you have here with let's say the generators of this group, and in the boundary we end up to having this kind of a limit set, which is usually a Cator set, which has this kind of like porosity that comes from the size of these holes, for example, that you see in this picture. Could have cusps or no, it depends. We'll have some examples with cusps and some without. Now, what I'm really interested at this talk, like the kind of main object of study, is the Laplacian operator here. And this will be actually interesting to ask, I will later on ask maybe people what would be the analog of this in the rational map. So let's talk about that later. But anyway, so we have a Laplacian operator, which is on just the hyperbolic plane. So this is the normal representation of it. There's a weight coming from the height in the plane model, and this is invariant under the group as a differential operator because these are Möbius transformations. The natural metric is here. So when it's invariant, if we have these generators, we can kind of glue and copy this operator as an operator that acts on pure gamma invariant functions. So functions that kind of like are folding up this construction in this picture with the kind of gamma periodic functions. So we get an operator on the surface. And now the object this is maybe the main thing that I want to understand are basically the scattering resonances, which are the poles of the meromorphic continuation of the resolvent family. So what does it mean? So basically resolvent family is what does it mean to be a meromorphic family, first of all. So what it means that that we take this operator, which is the resolvent, act it on, let's say, we have test function, let's say f and g, and we act on one and take an inner product with the other one. And we have then a complex function. We can have a function that we could try to define on some part of the complex plane and then extend that meromorphically. And actually it turns out that this meromorphic extension is independent of the choices of this test function, and the kind of poles that you arise are really intrinsic to the geometry and dynamics of this object that we have in the background, which is defined by the group. And it's actually quite a lot of information is captured by these resonances. And one application that people study this quite a lot is when they solve wave equations, for example, by taking representing the wave propagator using integral over resolvents, this kind of resolvent representation. And then if doing contour integration, you can pick up residues, and from that you can use those residues to study these types of resonance expansions, which gives some like heuristics of what this resonance is actually telling. My heuristics is more like it's a bit like a drum with infinite like ends. That it's you will not just have these standing waves that are staying on the drum, but they can slowly decay. They are like slowly decaying to infinity. So these resonance states are kind of something that you can hear from that are left from this infinite drum in a sense. So they capture some geometry. So what geometry they capture? How does the fractal geometry especially comes into play? That's the interesting question, I think, here. One example which I sometimes use, I think I got this on Maciej-Swirsky's lecture notes when he was teaching on these resonances, that they actually, in this case of modular surface, so if you use this integer matrices as the lattice, and these actually come by doing a spectral expansion of the resolvent action with the eigenfunctions, the Eisenstein series. From that picture, by the form of the Eisenstein series, you can find out what the resonance these are, and they actually come from the zeros of the Riemann zeta function. So somehow, like the idea here is that they should all lie on this part, where the imaginary part is actually equal to -1/4, except if they come from the L2 eigenvalues.
Is there some geometric interpretation of this kind of dichotomy that either you have these L2 eigenvalues, or either you have zeros of the zeta function? Is there any kind of interpretation one can give to this?
Yeah, I think so. That's the kind of I would imagine that's a similar kind of thing. I think how I a little bit see is that either the decay is 0 or it's -1/4, the rate of wave decay. These are the only two options. And actually now it's interesting that if we take a more general surface, not just a modular surface, here there's no limit set that's fractal, because it's just one cusp kind of simple kind of setting. So if you have these holes, then what do these resonances look like in this picture? Okay, the conjecture in this case is the imaginary part is -1/4, but in general that's not necessarily true. So if you take these Schottky surfaces, 3 funnel convex cocompact surfaces like you had in a picture, they look like this in this picture. And it's actually interesting that this goes to the back of this really the original work. Also, like basically this can be proved using the trace formula by applying trace on the scattering, like this kind of scattering matrix, and using the trace formula, you can actually prove this type of a result, that if the Hausdorff dimension of the limit set is less than 1/2, sometimes this is called pressure condition in the literature, if you want to read about this, then this X is an essential spectral gap. So that means that there are no resonances above this line. So in the Riemann zeta example, they are all just on the, conjectured to be all on the imaginary -1/4. So in here, like this picture around here. But for general surfaces, they can kind of like lie around everywhere. But you can always find one gap with the dimension theory. This is quite interesting connection already. But then the next level, can you take this a little bit further? Like, okay, what can you do a bit further about this pressure gap? And that's what we've been kind of interested in looking at. So let's improve this. That's actually quite challenging. I think there are many ways, but I think I would put Frederick Nord's paper as the really important work, as the kind of that gives really an improvement over this pressure gap. So you can slightly move the line down. You can't get all the way like to. Well, we'll talk about what is the possible optimal spectral gap, but you can slightly improve it. And he introduced methods inspired by these ideas of Dima Dolgopian from exponential mixing of geodesic flows and hyperbolic dynamics. And this method actually is quite powerful in a sense. It allows us to actually use this type of like an extra cancellations in the series to get a slightly better bounds. And in a sense that you get this like exponent that depends on something called Alphos-David regularity constant, the Patterson-Sullivan measure, which is basically that when you have the measure of a ball is less than a constant times r⁻s, and from below, then it depends on the c in the front and also the dimension. So it's kind of like depends on that picture. Then after this, maybe there are other works as well in between, so I'm skipping a little bit, but I think one of the main big improvement came in a work of Bourgain and Dyatlov and Joshua Charles in 2016, where they introduced this kind of tool from, it kind of came from like studying Fourier Integral Operators and microlocal analysis, and there was this notion of Fractal Uncertainty Principle, which is purely harmonic analytic statement between two fractal sets. And it's basically asking, when is a wave or wave function, can it be localized on a fractal set, both position and frequency? And the conclusion, it shouldn't be possible, but it depends on kind of what kind of fractals you're trying to localize into. And typically it should be some kind of porous set, a bit like these limit sets of Fuchsian groups that we see. This is actually a very interesting problem in high dimensions now, that this is very complicated, what is even porosity that we use there. But they got the improvements, and Laura Kladek and Terence Tao improved this improvement using some improved additive energy bounds. And this works quite well only at the dimension close to half. That's where this improvements made sense. And the induction of scales argument that they use for the additive energy are good there. But then now the question is that, okay, there is this high dependency on the Alford-David regularity constants. And now this comes closer to what the topic is of the talk is about, Fourier decay, that actually, if you use some product theory from additive combinatorics, and then just study Fourier transform of the Patterson-Sullivan measure, which would be the natural density at the boundary of the on the limit set, then using these tools and the kind of intrinsic multiplicative structure inside the Patterson-Sullivan measure, there is some kind of like phases are slightly distributed around the circle, that you get some kind of decay of Fourier transform. And because of this improvement and how this exponent depends on the kind of data here, the improvement only depends on the Hausdorff dimension of the limit set, which is basically also the Poincare exponent. So in a sense, like you can remove the dependency on the Alford-David regularity constant completely with this picture. This was like a very interesting way, and because it avoided the Dolgopiat method, which uses doubling of measures at some point, or I think he calls it Federer property or something like that. It's basically the doubling is important in that argument. So this is kind of what happened, but now the question is being that we've always assumed delta is less than half. What about delta bigger than a half? So the Hausdorff dimension limit set is bigger than a half. What can you do then? Well, in a sense, now the counter set you study is quite big. So maybe you could like try to compare it to the Lebesgue measure or something. Can you do something of this type? Like kind of, it's quite smooth. And actually, this was very difficult to do. And this in the paper of Bourgain and Dyatlov, in another paper that they had, they proved that there exists an essential spectral gap for every range. And it uses this Bernoulli-Malyoumi multiplier theorem to prove this type of a fractal uncertainty principle statement that I mentioned a little bit earlier for Alford-David regular sets. And it's a very and it gives you some exponent, and this has been some quantitative bounds have been given, but they're kind of far from what is expected as optimally the spectral gap to be. So this is kind of like the one-dimensional case. Okay, so moving on a little bit is now the optimal case. So this is kind of maybe due to a question coming from Jacobson and Nord's paper, where they kind of predicted that this optimal gap should come from this part, that the best improvement should be like a Hausdorff dimension over 2 instead of just some epsilon. So we already know that you can improve it by some number that depends on the limit set only, by Bourgain and Dyatlov using Fourier decay. But maybe you could push this further, that if you prove some kind of optimal Fourier decay or something like very good decays, then maybe you could get all the way there. And here's like a picture of the kind of what is known. So this is the dotted line is the Jacobson-Nord prediction. And this red one is the Fourier decay bound that kind of gets bad when you get close to a bit over half. And then the dotted blue line is what Bourgain and Dyatlov's paper did. And you can see that that bound that they get from Bernoulli-Malyoumi is actually worse than the Patterson-Sullivan gap at some point. So it's somehow like there's this king point that was currently known. But then there is this kind of numerics done on the essential spectral gaps. This is Nebothic-Weiss paper, that somehow it doesn't seem to support the conjecture in this way that you seem to get in this special focus. But maybe it's like the numerics that if you run it maybe bigger, then maybe you could like get something that would support the conjecture. But it's a bit inconclusive at the moment, how I understood it. But then at the same time, there is a paper of Dyatlov and Jean. So this goes really now to quantum chaos, but basically these types of things called cat maps, which are 2x2 matrices, for example, that are hyperbolic in a sense that they have one direction that contracts and the other one that expands. It's automorphism and just a matrix, but then you can quantize that to get another very high dimensional matrix, essentially. That's the dimension depends on some quantization parameter, and this is called a quantum cat map. And in this context, you can ask this, make it like open in a sense that there's possibility for leakage to infinity. And you could ask this kind of like same questions, like what is the optimal essential spectral gaps and these things. And this was actually kind of verified that these examples can be constructed where you actually see the optimal behavior. But then kind of like, okay, can you go back to surfaces? There's maybe something with the nonlinear phase that makes it difficult to actually apply this. But there was a recent work using random matrix theory by Irving Gauder, Michael Maggie, and Frederick Nord. So they study random Schottky covers. So take a Schottky surface, so take one, let's say, surface with these funnels, and then they take random high degree covers of this surface. They kind of prove this Jacobson now like kind of conjecture bound if you restrict to this kind of bounded frequency region. So you pick a compact region, any compact region, and then the probability kind of depends on this compact set. And then with high asymptotic probability, if the degree of the cover goes to infinity, you get this kind of plane that they have. And this is very interesting because it uses this kind of quite strong tools that have been developed by Sharpboard and now Benoit Collins on the strong convergence of random representations of the group. And this actually works quite well because these strong convergence theorems really naturally have the degree parameter into it, and they translate in this setting of the large degree of the surface. It's a little bit like a large genus or something like that. So yeah, okay, but this is kind of what's currently known. So this doesn't give the high energy things. You would have to kind of try to optimize the notions of decay. Okay, so higher dimensions. Let's move a little bit into higher dimensional setting and closer to what we've done. That was kind of the state of the art in the 2 dimensions, as far as I kind of know most of the things. So in high dimensions, now we could study Kleinian groups or even more general groups. So the kind of general setting that I want to take is a discrete, Zariski dense, convex cocompact group of isometries, the real hyperbolic space, d plus 1 dimensional space. So here, this word Zariski dense, I want to kind of emphasize, just means, so first of all, Zariski topology, you have the closed sets are like zero sets of polynomials. So when I say Zariski dense, it means that when we take the closure in this topology, you are not kind of like seeing something that would be like in a zero set of polynomials. Like if this is a subset of matrices, the entries would not be given by these zero polynomials, except it's the whole thing, which is the determinant 1, which is the kind of condition that you can expect from the isometries to satisfy. So that's like a Zariski closed thing, but it's only everything. And it basically, for me, yeah, yeah,
right. I mean, I was just going to ask. I mean, so why do you want to impose this condition?
Yeah. So it means things rotate, and it will come evident very soon that somehow it creates this kind of when you study Fourier transform, the Patterson-Sullivan measure, for example, later on, the phases start to like oscillate, like equidistribute, which helps a lot in this picture. And that's kind of the important in these non-concentration estimates that we need. And basically what Zariski dense for me is that it doesn't keep invariant, like these subdimensional manifold kind of shapes, like geodesic subspaces and stuff like that. And that's really important in the study to avoid that kind of situation from happening. So now we have the same thing, a limit set, some kind of a fractal object. We have a Patterson-Sullivan measure. We can define this. We have the resolvent operator, just studied the Laplacian on this surface or manifold actually that comes from here. But now the kind of critical 1 over 4 here is replaced by d over 2. And now the Patterson-Sullivan gap, the analogous version of this, if you do this kind of same theory with the kind of trace formulae and these things, then you would end up to this is the natural analog in high dimensions. But now the question comes, okay, we have all these questions. One dimension is what can be generalized? Well, a Gladek Tau paper was actually in high-dimensional picture already. They had the paper has two parts. It has the proof in one dimensions that's easier to follow, and you can get the main gist of the ideas, and then the high-dimensional thing that uses more elaborate estimates, but still working quite well. That if you assume the dimension is close to d/2, you can improve these types of additive energy bounds that they were using in this kind of similar fashion, but it's more elaborate. So that's possible. But then the kind of Dolgopiat method kind of question that can you do like Frederick Nord kind of did in this picture. There's a paper Bacchus, Leng, and Tao that actually apply directly the Dolgopiat's method in this picture, and they can improve the spectral gap. But now it depends on the doubling constant, like we kind of expect it should depend if you use kind of this Dolgopiat method. But it also depends on some non-concentration conditions of the Patterson-Sullivan measure, which are kind of related to think that Patterson-Sullivan measure could, I guess there could be examples that it would like put a lot of mass in a lower dimensional part of the space. I don't understand that yet completely, so I'm trying to learn this high-dimensional theory, but there's some like possibility of Patterson-Sullivan, some examples that you can construct some crazy groups that could do this in high dimensions. But that's kind of the problem why they need to impose this assumption. But now the high-dimensional analogues of this, when the dimension is bigger than d/2, but this is actually still kind of in progress. There have been some major work done on this recently, like especially this paper of Alex Cohen, and then also the earlier paper of Han and Schlag, where they study something called this fractal uncertainty principle, but for porous sets that are products of porous sets, a bit like Cantor dust. And then there is directionally porous sets that come. I don't know whether this is what is this? This is porous, but maybe this would this apply in their setting, but that's the Menger response kind of thing. So it's kind of like a progressive, but this especially this Cohen's work was important because the challenge is to generalize into high dimensions what is using this Bernoulli-Malevich multiplier theorem. When it's a product set, it was possible to kind of use the projections in a suitable way to apply the one-dimensional ideas, but then somehow the truly high-dimensional thing was requiring really new input. So this is a big breakthrough by Cohen. But then now the remaining question that we are addressing here is how to make this improvement kind of basically independent of the doubling constant, which is kind of like the high-dimensional thing. So we need the Fourier decay. So first of all, in the PSL2C case, the Kleinian case, this was done by Lee, Nord, and Pan in 2017. And now recently we did this with Simon Baker and Osama Khalil. So we do this improvement that is independent of the doubling constant, but there is this non-concentration property of the measure. So this is the kind of like how much mass does it give to hyperplanes in this small sense. So what we can get in this setting is basically the power Fourier decay of the Patterson-Sullivan measures, and that's the kind of in a similar spirit as the Bourgain and Dyatlov did. But then actually this work was really coming first from Osama's. He had a preprint by himself on arXiv. And then we noticed this, and at the same time we were working with Simon Baker independently on kind of towards this similar goal. We had also some other examples we were interested in studying, like more general self-conformal sets and self-similar sets and self-affine sets. And we noticed actually the kind of similarities in these kind of approaches, and we then kind of combined these ideas and managed to get this kind of like more general actually framework to actually study Fourier decay of any types of stationary or dynamically defined measures using these similar tools. So this kind of work also has the kind of more wider context, which I a little bit want to highlight in this thing. So if I have a little bit of time at the end, I will talk a little bit about the proof, where you can see how the flattening and what is this, what are the hyperplanes and this concentration, how they come into this play. So you will get some idea what the thing is. But it's like a general framework. And the kind of I just want to mention one thing about the paper of Lee, Nord, and Pan, and then because they studied the like PSL2C case, so you need some analog of some product theory in this setting, and there's some multiplicative structure of the Patterson-Sullivan measure. And that was done by studying some product bounds in real Lie groups. And that was by a paper of he and Desachse. And that allowed them to actually kind of study a specific version of the that theory that works quite well with the certain groups that you can do in this context. But it's quite specific for this setting, works well in C because of you can kind of use the real part and that for the in a product or in a right way that works quite well in here. But in high dimensions, we cannot use that. We have to use this this kind of flattening approach. That's why it actually was kind of open. What can you actually do in high dimensions than this complex plane PSL2C case. Okay, so now that's one result, and another one that I want to mention before I go to the Sullivan dictionary part is the parabolic case. So let's go back to the limits as in hyperbolic surfaces, so not manifolds as the two-dimensional surfaces, but let's add parabolic elements into the group. So we have some kind of cusps in the surface, essentially. Okay, what to do? This actually complicates quite a lot of the theory and matter, and what can you do? And it's a little bit like a complex, but we can prove a powerful decay at this case as well. So but it requires us to actually go to step away a bit from the study of the Bourgain and Dyatlov, how they approach this, and then try to use a specific coding for the Patterson-Sullivan measures to achieve this. This was done. This coding was introduced by Lee and Pan in one of their papers, where they studied more general, geometrically finite. They studied the mixing properties of flows there, and this coding was actually very convenient because it had the right properties we really need for to build the thermodynamical formulas and then create the kind of environment where we can use some product theory in a similar fashion. So that was actually thanks Jielu Lee and Wen Yu Pan for this paper, but then the point also was that we didn't just restrict to the Patterson-Sullivan measures. This is not really needing so much. It's given by some group, but actually it works in very generality in any kind of parabolic systems like the Manville-Pomel maps and some more rougher examples that we can work on. So it's really more like whether you have this kind of cosine structure. And this actually becomes important when I want to talk a little bit about the possible analogues for more general maps that quasiconformal geometry. So okay, that's the kind of parabolic case, and now the Sullivan dictionary analogues of these questions. So take a hyperbolic rational map of degree at least 2, and then you have these Julia sets, and here's a picture of lots of Julia sets picked from the Mandelbrot set. You can kind of see how they change when the C changes in this thing. So they should look like a circle near the middle, and then there's the parabolic part near the end of the Mandelbrot set, and then there's all these other ones, and there's measures you can put to the boundary, like the measure of maximal entropy or the conformal measure. So there's lots of different measures in the study that kind of see the similar way as the Patterson-Sullivan measure the fractal geometry of the boundary. Okay, we can ask the question of the Fourier decay, and we actually studied already in the 2020s with my PhD student Connor Stevens the case just that if it's contained in a circle, so it's like a Cantor set inside a circle for a rational map. And in that specific case, this has powerful Fourier decay, so we kind of were able to prove this type of a result. And this used some spectral gaps for twisted transfer operators, which is basically some bounds that Frederick Node also got for certain transfer operators. We adapted these spectral gap bounds to get the right non-concentration properties, which we could feed into the Bourgain's discretized sum product theorem bounds. But this has been now generalized to different directions. There's a lot of papers on this, which I'm probably going to miss now, but especially by Amir Algom, Frederick Rodriguez Hertz, and Shiren Wang, and other people, Simon Baker, and Amlan Badanji, and I'm sorry if I missed a lot of names. It's just there's a lot of different generalizations how this goes. But then for the complex Julia sets, this was done by Guyot and Leclerc. That when it's not contained in a circle, like this in these pictures we saw, like all these other Julia sets, these require adapting ideas of Ohan Winter from prime number theorems for hyperbolic rational maps So in that, they studied this type of spectral gaps as well for these twisted like transfer operators, and then it kind of adapted in a similar fashion as the Linod and Pan also used this some product bounds from real Lie groups. So then Leclerc found a way. So this is kind of in the spirit of the Sullivan dictionary. Okay, you can use some tools from the same setting, but then do a different idea. And the key why you can use is the Markov partition can be constructed here, and you can kind of use the same thermodynamic setting. So the coding is so important actually in this picture. So now the problems, let me pose a couple of problems that maybe you could study. So do the parabolic Julia sets have positive Fourier dimension? This doesn't follow any of these works. And again, given the fact that we had this Fourier decay for Patterson-Sullivan measures on the geometrically finite setting, then by this analogy, this should be possible for the cauliflower, which is for example, this one or other kind of parabolic, when there's parabolic fixed points. Another much harder question, probably impossible, are these Salem sets. Does a Salem set is a little bit, this would be motivated like going this Jacobson node type of optimal spectral gap bound that I talked earlier, that if you can optimize the Fourier decay, this immediately feeds to better bounds for the essential spectral gap. So the kind of optimal rate of Fourier decay you expect actually is Hausdorff dimension over 2, essentially, maybe plus epsilon, that depends on epsilon. So for any epsilon, this Fourier decay is like almost optimal that you expect. This is actually interesting. There's some numerics which seems to like support at least partially these types of things. But I think that again, the numerics is kind of you might need to run it to with much higher frequency to really be more confident that can this actually be done. This would need some new ideas completely. Like this, something like the bounds exponents we get quantitatively are very far from this. But then maybe some kind of an induction or some kind of bootstrap or something that you could maybe amplify the Fourier decay to a better exponent. Maybe something could be done. And finally, is the problem that actually related to this, that this was asked independently by Jonathan Fraser and Kai Astola, who's also here, we sometimes chat, and he was interested in this problem, is that actually there's this case of a circle, which is a Julia set for the Z square. So in the picture, it's kind of right in the middle here, like kind of in the Mandelbrot set. That's a Salem set because it's a circle, it has curvature. So when you integrate by paths, the Fourier transform, the length measure there, which is the one-dimensional Hausdorff measure, decays polynomially exactly with the exponent Hausdorff dimension over 2, which is 1 over 2. That's an exercise. You can check it from even, I think it's one of books of Pertti Mattila, you can find this. But now if you take a quasi-disk like nearby this, so you just take a one perturbation, immediately you cannot, everything just collapses somehow. These proofs that I've mentioned, these methods, they all like kind of use some pseudo-randomness, that they iterate somehow the dynamics many times to create some randomness, some convolution structure. And then they can use these sum product bounds that give you some kind of Fourier decay, which are very non-quantitative. These are really like far from continuity. So I don't know, it's like it could be that this could be a one avenue to try to first study this problem and then maybe try to study more general. That is there some tools that you could use from holomorphic motion maybe to attack this problem? I don't know. Then come even the more speculative slide. So some prospects for quasi-regular mappings. So what if this F is not anything like, let's say we are in some like even less regular setting. It's like a Sobolev map or something like this, and so it's like the derivative can be constructed and like weakly or something of this type. Well, what we did in this paper with Leclerc and Paukkonen, which mentioned the same paper we studied the Patterson-Sullivan measures with parabolic thing, we did study actually maps that are truly Hölder derivatives. So they had this like C1 plus alpha regularity. So these are like kind of cases that no other paper like kind of really could study before in the same context when you have this nonlinearity, when you have this only weak regularity. But we need the C1 because we use the chain rule. We need somehow the F prime. When you take a composition of maps, then we need to know what is the F prime derivative. Becomes a product, and because it becomes a product, we can use multiplicative convolutions and the additive combinatorics in this proof. So if you want to generalize this to like uniformly quasi-regular maps on this D sphere, which would be maybe kind of like a high-dimensional analog of these rational maps, maybe in this setting you would need some kind of derivative cocycle. So an analog of log of the derivative prime, maybe using the local Lipschitz constant at some point, and then trying to prove that it almost has a product structure. It doesn't have to be exact because the errors are okay to be absorbed into the proof sometimes. So maybe you can like approximately use a chain rule in the same way. I'm not too familiar with this problem, so I've been trying to talk to some people who maybe know more about this. But then in the case of this S2, there was these papers of Li, Shi, and Cheng that actually studied kind of the analog of these all-winter prime number theorems, and there was these twisted transfer operators for expanding Thurston maps. But then the problem here, like kind of, I think, if I understood correctly, I think there are people in the audience who know much more about this, but the limit set is everything. So there's no fractal. So in a sense, like high dimension, if you go to like UQR maps, like dimension at least 3 or something, then maybe you could like have these like actual fractal measures in the in that setting that you could maybe try to generalize some of these ideas, and that would be like the one avenue to try to attack this problem. Okay, so that's kind of like part one of my talk, which is the kind of results. And now I could go a little bit into the proof, if that's okay. I think I have like, is it like 15 minutes or something like this? Or
yeah, 15 minutes.
Yeah, that's good enough. I think that's enough. Let me skip a slide because I wasn't sure how much time I have. So I said would be the end, but then thankfully it's not the end. So we have some proofs, ideas. So let me give you the main strategy of the approach in high dimension. This is maybe the one that I want to mention. So the first step you want to do that, okay, we want to prove power Fourier decay of something, whatever it is, like a Patterson-Sullivan measure or other measures of this type. Then let's first prove something easier. Prove that the Fourier transform decays almost at all frequencies, that there could be some peaks somewhere, but we don't really care about them. We just want something called average Fourier decay first. And then it turns out that by using chaos, the kind of non-commutativity of the group later on, this helps to then amplify this to actually a full decay. That's the idea that we use with Osama Khalil. So I'll show this now how this works. So what is average Fourier decay? So let's take any measure. This becomes now geometric measure theory talk for a few minutes. Any measure on RD. So if you have a measure on RD, the Fourier transform of this measure is defined by this quantity, this complex number. We've seen this already. And then you can see somehow the inner product appearing in this exponent. So there's kind of like something that maybe if there's like a concentration of the measure on like a lot of the subspaces, this will be picked up by this quantity. So it's not a surprise that, for example, if you take a length measure on a line, that the Fourier transform of the orthogonal direction doesn't decay at all. It will be like a Dirac mass on that direction. So you need to really avoid concentration of subspaces to have this thing decay in high dimensions. And even in one dimension, your enemy is something very, very subtle. It's not just, okay, one dimension kind of lines up points, but actually there's something more that is your enemy in one dimension. And that's kind of the complication in high dimensions as well. It's kind of like a dynamical, like a resonance of certain measures. So let's take a self-similar measure in the middle of a countermeasure. And actually it turns out that self-similar measure is just the measure that's natural half-half weight on both construction paths. And if you take the Fourier transform of this measure with this formula at the frequency 3 to the power n, it's invariant under this. By the fact that the middle of the countermeasure is invariant by multiplication by 3, plug that in, you get this, that it's actually constant function along. So the peaks will actually just repeat up to infinity. But then Masato Chui proved in 2012 that for self-similar measures, there is an average Fourier decay, power decay. In this way, you can use these covering numbers essentially to state it. That if you take any epsilon, then there is a kappa such that for any large t, this set of peaks, which let's call it like a spectrum of the measure, is small. So the spectrum has to be quite small. And this uses the autosimilarity of the self-similar measure that, okay, yeah, there are peaks, we saw 3 to the power n, but these are like lacunary in a sense that they appear very rarely. Most of the time you see power decay. So, okay, that's actually quite interesting. And this is actually a manifestation of something far more general. This is the high dimensional result. That's the engine behind our theorems. average Fourier decay for non-concentrated measures was proved by Osama Khalil recently. And this is the definition of what do I mean by a measure avoiding subspaces, maybe answering slightly to Mario's question that a measure on RD is uniformly affinely non-concentrated if at all points and at all scales, the measure doesn't want to look like a plane. It just looks like something is always going to every direction in some level. So, but you can do it by this measure, like kind of like an Alphonse regularity, Prosman condition on tubes. So if this would be in 2 dimensions, this would be like a tubes don't want to carry too much mass in the terms of the measure. So if you have this condition, you precisely get the same analog as Chui gets for this. And this has no assumption in the measure. Can be even any measure that has this condition. So it's just that these covering numbers, instead of using like intervals, you use cubes and then cover it, and then the kind of bad peaks are very rare in terms of the covering number. And that's how this is related to something called L2 flattening I've talked about. You can use basically this idea. So you can discretize the measure on RD into dyadic cubes of cycling 2 to the power minus k. And when you have discretization, it's a discrete measure. You can define that it's non-concentrated if the L2 norm is kind of small. That it's like if it's large. And if it's small, then it should be very highly concentrating in the space. So the L2 norm measures somehow the concentration of this measure, like every direction. And the flattening theorem is this. This is the kind of that implies actually this result. Is that if you have a uniformly affinely non-concentrated measure and you convolve the measure's discretization n times with itself, it will start to have even more like spreading. So the L2 norm has this kind of like a bound that you can have in this way. So there's like kind of like you start from something that might be quite concentrated, but then if it has this non-concentration affine subspaces, when you convolve, this actually makes it to spread even more. And this is kind of like a central limit theorem in high dimensions, but more quantitatively and kind of better in this way. So that's why it's held for any measures. And how this implies the average Fourier decay by Plancherel theorem and convolution theorem and a lemma from Berti Mattila's book. It's one-line proof. So you take the set of bad points, take the Lebesgue measure of this point, and multiply them by some very small constant. Then you bound it by the integral. That's just because that thing is bigger than this number down here. Use the convolution theorem. Fourier transform convolution becomes the product. And then you use basically, this is Plancherel's theorem application here, that you can translate the Fourier side into the geometric side. So this is a lemma in Mattila's book, for example. You get this integration of poles of radius 1 over t of the convolution. But actually, this is by the covering with these dyadic cubes. It becomes the L2 norm. So you just kind of can get from this kind of random walk theorem into Fourier decay theorem by this one trick. So how this kind of then works in our favor, the Patterson-Sullivan measure, for example. So now we see kind of like how this goes. So let's take a dynamically defined measure like the Patterson-Sullivan measure in the high dimensional setting. Then we have these 3 steps in the proof that are really driving the whole strategy. So the first of all, we use the autosimilarity or the stationarity of the measure to express the Fourier transform as an average over some other Fourier transforms on some other measures at different random frequencies. Typically, these measures are basically the same as the original measure. If it's like self-similar or some kind of a very nicely conformal measure, they're almost the same as the original measure, but they kind of have a random frequencies. And the point is that somehow these random frequencies are sampled by the actual original dynamics. So if the original dynamics, like the Patterson-Sullivan measure, the Zariski dense property, for example, there's like rotations, these are actually quite well spread around the space. So this actually will be useful later on when we combine it to the flattening theorem, that when you do this covering lemma, that you have like frequencies of many places, so then bad frequencies can't overlap too much with the ones we try to study. The second step is this flattening, that you apply this kind of flattening theorem for these measures. You try to check that they are uniformly affinely non-concentrated. That from Patterson-Sullivan measure, this kind of is possible by using the stationarity. you can also get this for the kind of blow-ups. It's a little bit involved that you can do that with thanks to the stationarity. And the final thing is some Diophantine property, also similar to nonlinearity, that really makes this random frequency spread out in a space that actually, by some pigeonhole principle approach, that they don't hit these bad ones. So then this average of Fourier transform, actually the whole thing decays. It's like splits into two parts. The ones that are like the bad frequency are good ones, and on the good frequency you have a power decay or some other decay, and then the bad ones are like in a very small set. So that's the basic strategy. And because I have still a couple of minutes, I'll do the case of self-similar measures on the real line, that you can see this really concretely what this whole thing is, without going into any kind of, you can actually follow these slides, especially if these are recorded later on, you can look at these slides. So you have an IFS, which is iterated function system, the real line. Let's say contractions could be like 1/2 or 1/3, and given by two translations, and you choose them so that these log ratios are Diophantine numbers, that they don't want to look like rational numbers. This will be the important Diophantine condition that creates chaos in the system. So for example, if you have a log 2 over log 3, that's a Diophantine number. So it doesn't want to look like a rational number at all. But it still eventually converges, but it's very slowly. By Dirichlet theorem, we know that these things do converge eventually. We can approximate any rational, but it's very slow. Then we take a self-similar measure on the real line, and then we can actually iterate this and use basically this kind of partitioning of the tree, that the self-similarity is typically written that you kind of use the tree into two, like, let's say, cylinders. But we can actually split it further on in sub-cylinders, that if you have some kind of something called a stopping time condition, that some condition on the verge that something is needed to have the boundary decay, then you can split the tree into this kind of like a self-similarity. I think this is something also called an optimal stopping theorem for martingales, that you can write this. But basically it follows from this by iterating this, and then sometimes if you have a cylinder, you have some condition. And the condition of the verge will be something about how they relate to the frequencies. So let me show this, how these steps go. So we take a measure, this frequency, and have this self-similarity, iterate this. So this is the averaging. We just apply the previous thing, and this is the condition on the verge, that the kind of contractions times the frequency are roughly the same all the time. So sometimes the length of the verge might be bigger because you're sometimes, let's say, dividing by 2 more, dividing by 3 more. So sometimes the verges are slightly bigger. So you have this kind of fluctuation. And then you do an inequality you should probably never do, which is like put the absolute values inside, and you probably lose a lot of cancellation here. But it's actually not so much that we actually can use this. So we have these measures with random frequencies given by these. So these are the random ones that I mentioned. Then the flattening, you just check that, okay, hey, by the way, this measure is self-similar measure, so it satisfies the conditions of Khalil because it's uniformly perfect. Uniformly perfect would be the same assumption as being avoiding subspaces of points in the real line. So it satisfies the assumption because of Alford-David regularity, so you can use that. And now you can split the Fourier transform into two parts. So you cover the frequencies by the intervals which are like the bad ones and then the good ones. And in the complement one, we actually have polulogarithmic decay. So this is a way to prove not power decay, but polulogarithmic decay of the self-similar measure in this way. That actually split the frequencies into the part where you hit, let's say, the kind of exceptional bad frequencies, and then the good ones are the complementary ones. So here is basically you bound by the Fourier transform by 1 for the ones where you're in the complementary part. And you just need to bound this. So what happens here is that basically this thing we had earlier is split into two sums. So we split the integer into two parts, and we have this bound. And now there's no measure anymore. So this kind of is just a purely combinatorial question. How is this bounded? And when it's a combinatorial question, and these are to do with some kind of products of contractions that are coming from integers that satisfy some Diophantine properties, then you can use separation. So this is the Diophantine assumption coming into play, that somehow, basically by pigeonhole principle, only one of these essentially hits one of these intervals, so there's some multiplicity going on, but not too much of the multiplicity. And if you do these differences of two different words, then they're actually separated by 1 always, except that if you have this number of words. So this means basically, what I mean by this is basically the numbers of because these are given by ones and zeros. If you have two contractions, then some of them will be like there's some different that we are using, let's say half a bit more times than the third, and that the rational number is just counting the number of let's say zeros and ones between the two different worlds, and that's how we can make this kind of comparison. And because of the time I'm literally running out now, let me just write this with this slide. So if we do this kind of counting argument, we see that actually if we count all these number of different possibilities, we get some binomial coefficient, and then by some Stirling theorem of how many there are, actually it turns out to be very small, and because of the flattening, we can make the exceptional set as small as we want. That can be like whatever exponent we get from the Stirling's theorem is enough for the bound. So this is like in self-similar measures, you see the strategy how it goes, and in high dimensions you kind of include the rotations into this picture. But that's all I wanted to say.
Yeah, thanks a lot. Yeah, let's thank Tuomas. And let me start the discussion. Are there comments or questions? Yeah, can you maybe go back to this holomorphic motion question?
Oh yeah,
I mean, this is a very intriguing.
Yeah,
right. I mean, an obvious approach is maybe to try the conformal map on, if C is close to zero, of course you have a quasi-circle, right? And there's this conformal map from the complement of the unit disk to the, this could be a potential approach to getting your hands on the Fourier transform.
So you map it with the conformal map, maybe the measure from the disk.
Yeah, I mean, if I remembered right, I mean the measure of maximal entropy, I think it's just the push forward of Lebesgue measure under this conformal.
Oh yeah, that's true. Yeah, that's good.
And the map depends holomorphically on C, right? I mean, I don't know. I mean, it seems that you should get something out of this immediately.
That's
too naive, right?
Yeah. This is something with the higher frequencies that somehow it gets more and more sensitive to the something that I tried a little bit with hyperflow. If you study this on the in the other side, so the group side, and I take like parameterize these Schottky surfaces, then something like I wasn't able to control somehow the maps between these two spaces. But I think I need to really get into understanding a little bit better how this whole thing works. And
yeah, let me ask you another question. I mean, this one-dimensional example that you discussed towards the end of the talk, right? I mean, this was a nice introduction to these kind of techniques. Is this written somewhere? I mean, except now in your slides?
Yeah, it's in the paper where we do high-dimensional version in the paper. So we wrote this in the beginning of the proof to like kind of for the readers to get more into understanding it, because the Patterson-Sullivan proof, for example, is quite involved. It involves a lot of the kind of algebraic methods in the proof. So this was maybe somehow more user-friendly, especially.
This is very transparent. So this is in this flattening paper?
Yeah. But it does the rotation, so it includes the rotation, but it actually just use the diaphony properties of the contractions. So I think it could be amplified if you study spectral gaps and rotations, but there's some open problems about which are actually quite difficult at the moment. So on random walks on the SOD, so these are actually not so clear what can you do. Only for diaphony random walks by some paper of Benoit and Nicolas Desax, it has some work on those.
Okay, so are there other comments or questions?
It might be a very silly question, but so what's an example of a quasi-circle that's not a Salem set besides? So, of course, like if it's a polygonal curve, then obviously it's not a Salem set. You don't have Fourier decay, but then say your Markov snowflake, is that a Salem set? I mean,
I don't think it's known, and actually I think maybe some example of that time, maybe then if you can construct a bit like the middle dot countermeasure, some kind of dynamics that would behave a bit like this, that there's some Fourier transform to this direction is invariant under this object. Maybe the coordinate snowflake could be made into this type of an example, but it's usually you need some kind of rotations in the dynamics to have powerful Fourier decay. So then it could be like something where you don't rotate too much, are they?
But so wait a second. I mean, if I understand it right, the von Koch snowflake should not be a Salem set, right?
Yeah, it should not be. Yeah, that's the. And also, like there's examples of self-similar sets. If you use, well, of course, we have the Middleton-Cantor set, but actually any Piso number, if you have a contraction, then they don't even have any decay. So that's if the contraction is a 1 over a Piso number.
So the snowflake is not a Salem set because it basically, I mean, has like some preferred directions. Is that the right sort of?
Yeah, but I still don't think it's proven anywhere. So that's the thing. Like it should be done. But I really strongly think it should not be Salem set. There's be some twisting, like in the quasi circles, like maybe applying the Julius. It's something that rotates a lot, and then that's needed in proofs.
I mean, you can sort of turn this around. I mean, like what would be like, I don't know, let's say a holomorphic motion or where the Fourier dimension or what would be, I don't know, let's say continuous, or, could you sort of cook up an example where, like let's say the Fourier dimension or what would be sort of continuous or something like that?
Yeah, that's actually only the main examples where you can actually get some continuity are random cascade measures. So if you study random fractals, then you're immediately away from the problems of pseudo-randomness that you need to iterate the dynamics a lot. So let's say take a Mandelbrot cascade measures. These are these papers of, there's, for example, recently some work of Garban and Vargas, and then also later on this paper Suomala, Chen, and other people that study like the cascade measures. And because they have multiplicative structure built into them by the IID, they are Salem measures. So they produce Salem sets very easily.
So if you have, let's say, like SLE curves or which are, random.
So probably.
And I mean, I mean, philosophically, they should not have a preferred direction. Would that? I mean, I have no idea how one would prove that.
Yeah, they should be Salem, and I think maybe you should be able to apply the methods of this what Garban and Vargas, for example, did. Maybe by studying Gaussian free, maybe this type of like more field versions of this. I think somehow from that picture you should be able to prove that these SLE curves are probably Salem. Almost surely. Like
Yeah, sure, of course.
Yeah.